Okay, YouTube, in this video we're going to look at an application situation with linear programming in which we're going to have to set up our variables and constraints and objective function first and then proceed with carrying out the steps in linear programming. So let's go and take a look at this problem here. And while we're reading through this, let's underline crucial information. Keep in mind, however, the first thing we want to do here is write our objective quantity, or the thing we're trying to make as big or as small as possible. So let's read through this here. It says a company makes two models of DVD players at costs of $250 and $400. It says the $250 model yields a profit of $45 and the $400 model yields a profit of $50. Estimates show that the total monthly demand for DVD players will not exceed, I'm going to underline that, 250, and the merchant does not want to invest more than $70,000 in inventory for these products. It says find the number of units of each model that should be stocked in order to maximize profit. So let's start with this. It says find the number of each model that should be stocked. And so how many models are there? Well, there are two models. So we're going to start with our variables here. And our variables, which we always usually start with when we talk about an application situation, always represent numbers here. And I noticed that there would be two. So we have number of and number of. And in this case, we say models, and we'll say $45 model. Actually, no, it was a $250 model, wasn't it? $250. And then the number of these models here that are $400 a piece. So now that we have both of these down, know that X and Y represent not dollars, but the number of models that we have that we should produce at each of those costs. Or I guess, yeah, that would be costs. Or DVD players here. So we have our variables defined. Let's talk about our objective quantity. So I want to talk about our objective function. So now in the past two videos, you've seen me use Z as our objective function letter. We say this function here that we want to make as big or as small as possible. In this case, I read through this and it says, okay, find the number of units of each model that should be stocked in order to maximize profit. What gives it away that I want to talk about profit here is the fact that it says maximize that. So since we're maximizing profit, what we're going to do is we're going to write an expression for profit. And I'll actually just write P. And what I know is this. They told us about profit. For every one of these $250 models we sell, we get a profit of $45. And for every one of these $400 models we sell, we get a profit of $50. So if I wanted to find my total profit, I suppose I would say, well, $45 times however many of these I sell, plus $50 times however many of these I sell, this would represent how much profit goes into our pockets. Okay. So here's our objective function, and that measures our profit. That's what we're trying to make as big as possible. So now we have this. Let's develop our constraints. Now constraints, when you read through the problem, in these cases, we're going to look for phrases like will not exceed, or is at least, or will be no more than. Okay. So in terms of constraints, we're going to go ahead and start with a critical set here. X is greater than 0 and Y is greater than 0. If you're going to make a little note here, we're going to say we have non-negative values. And the reason being is because when you look at your variables over here, how we define them, I'm not going to get negative models of each type here. So we're going to say we're in the first quadrant. Now, what else we know is it says estimates show that the total monthly demand for DVD players will not exceed 250. So the total monthly demand, okay? Total. How do I find the total of my DVD players if I have X of them over here and Y of them over here? Well, what we would do is we would say the total of my DVD players is this. So instead of writing 250, which equals 250, which is what we're used to with systems of equations, the fact is it says will not exceed. So when we interpret this here, I certainly have the total is 250, but when I say will not exceed, it's important that we say that I'm saying it's less than or equal to 250 of those. It also says that the merchant does not want to invest more than $70,000 in inventory for these products. So in terms of what they're talking about here, they're talking about the cost to us. Okay. So in inventory, we know that it's $250 for every first model and $400 for every second model. We say 250 times the number of things that cost that amount plus $400 times the number of things that cost that amount should stock no more than $70,000. And so these are our constraints for our problem here. What we're going to do is we're actually just going to go ahead and graph this. And so my favorite part of this is that I'm not using grid paper, and I say favorite because I can just go ahead and tell you right now y equals 0 and x equals 0 are a couple of our constraints, and that they shade out here into the first quadrant. I'm going to put my arrows in later, but basically we're up here. So when we graph both of these, let's go ahead and do this first. Before I graph these, because they have bigger numbers, what you're going to want to do is find your intercepts up front. And the reason why is because we're going to have to choose a scale for our x and y axes here. So I know this. If I plug in 0 for x in this first equation, I get 250 for y, 250. And I get 250 for x if I plug in 0 for y also, because x and y have the same coefficients. But here, a little bit different. When I plug in 0 for x here, I get 70,000 divided by 400 is my y value. And so let me get out my calculator here. 7 with 4 zeros divided by 400. So 7, 1, 2, 3, 4, divided by 4 with 2 zeros, we get 175. And I just want to check this again here. So 7 divided by 400, 175. So we get 175 here, 175. And then when we plug in 0 for y, we get 70,000. So 70 divided by 250. Ooh, that is 70,000. 70,000. There we go. Divided by 250. 7, 1, 2, 3, 4. Divided by 250. 280. Okay, much better. Human error, right? So we'd say it looks like we're going to have to go out to at least, I would say, looking at these values, maybe 300 each way. So what I'm going to choose to do here is this. You know, I'll go by 50. So 50, 100. 50, 200, 50, 300. And I'll do the same thing here. 50, 100, 50, 200, 50, 300. So we get 300, 200, and 100. So we're going to go ahead and graph these constraints now. And I would say that graphing these two here, we'd say the 250 and 250, that would have to lie right here and right here. And so kind of sketching this in, we know that we would have this constraint that runs this way. We know that we would want to label this x plus y equals 250, and then go graph our other constraint. And it, simply put, you know, its vertices are at 0, 175. So here is 150, here's 175 right there. And 280, we'd say 250 is right here. 280 would be, you know, beyond that out to here. So I'm going to, as best I can, freehand here. That's not working. Okay, we'll try. I'm on the right course. There we go. This here. And I'll label this one. How about we label it up here? We would say that this is 250 x plus 400 y equals 70 grand. Okay, so with this right here, basically we're going to want to test points and make sure we shade appropriately. I know because I'm shading up here on the first quadrant that I'm going to be kind of in here in this general region. But also I know that when I test 0, 0 into each of these equations here, for instance, because they're both in standard, you know, on this first one here, I get a true statement, but the whole left side collapses to 0. So we get 0 is less than or equal to 250, which is true, but also down here I would get 0 is less than this very large positive number. So we are going to shade inward towards that point 0, 0, and then look for our feasible region. So here's the thing with our feasible region, and as I've been doing, I'll switch my colors here. We would say all of the points in this problem that satisfy these initial conditions that we imposed on ourselves, these constraints, have to lie kind of in this area right here where all of our arrows are shading together. And where it gets kind of important to be careful is when we look over on this right hand side, because there is a vertex value right there. Excuse me. So our 4 vertex values are these 4 that we see here. What we're going to do is we're just going to go ahead and create our optimization table. So we would say our vertex values over here, x, y, and then over here we have our profit equation. Our profit equation was 45 for every x and 50 for every y that we sell. So with our 4 vertex values, let's go ahead and put these in. We have 0, 0, 0, 0. We also know this one right here, just due to an intercept, was 250, comma 0. I can see that actually this is 280, 250 right there, 250, comma 0. Up here we knew this was an intercept. This was our 0, comma 175, just because it was an intercept we saw over here. So I'm going to put these in here. We have 250, comma 0, and then I have 0, comma 175. So now this last one right here, what we're going to have to do is solve a system between the 2 equations here. So we know the 2 equations that intersect there. We have x plus y is 250, and we certainly have 250 of these x's plus 400 of these y's, equaling 7 with 4 zeros after it. So now, let's do this. Let's take the top equation times negative 250 and add it to our second equation. And what we would get is this, 250. We'll have to use our calculator here. Negative 250 times this plus this would get this to cancel, but negative 250 times this here would be negative 250y's plus 400y's is 150y's left over. And then here's where I'm going to need my calculator. If I said negative 250 right up here, 250 negative times positive 250, and then I add that plus the 7 with 4 zeros after it, I get 7,500. So 7,500. So what we can deduce from this here is that 7,500 divided by this 150 right here, divided by 150, that's how many y's we should produce. We say 50. And if I know y, then we could go plug this back into the original equation up here. One of them, we say x plus y, which is 50 here, would be 250. And what we found out here is that x is equal to 200. So I'm going to put boxes around these. I'm going to say that this point of intersection right here is 200, comma 50. So 200, comma 50. And I want you to think about this as we get ready to plug these all into the function. Which of these points is going to give us the maximum profit? Where would it have to lie in your feasible region? If you're looking at your feasible region up there, where would the xy value have to be in this region here to, when we plug it in, make this as big as possible? And what I would argue is it would have to be as far away from the origin as possible. So when you plug in 0, 0, the whole point here is that you get a profit of $0. But when we plug in, say, 250, comma 0, let me open this up here. 250, comma 0, 250. We might be able to make it through this without my graphing calculator. We say 45 times 250 is 11,250, and then this is going to be times 0, so we get 11250. When we plug in 0, 175 here, I'll take 175 times 50. We'll get this value. So 175 times 50 is 8750, so not as much as what we saw right here. And then this last one here, we say 250. So I think I can get this here. If we doubled 45 and added 2 zeros, we'd have 90 with 2 more zeros. So we'd have 90 with 2 more zeros. So that would be this here, 9,000. And we'd say 50 times 50 would be 25 with 2 zeros. So we would get 11500. Yes. I'm going to put a box around this because this is our maximum value of the objective function. So here comes the conclusion statement, basically what we can draw as a conclusion from this. But this one's a little bit different than the last two because we actually have variable values. So we should say this: a company should manufacture 200 of the $400 models and 50 of the $250 models. And I just got this from right here, our objective values right here, 250, and my variables over here. So 200 of the, and actually I've got this backwards, our x value is 200, and that was our $250 model. So I'll go back and fix this. So 200 of our $250 models, and then we would say that if I wanted to change this, we would produce 50 of the $400 models. Okay. The last part of this, it would be this: to make a maximum profit of. So that's that. That's how we use linear programming to maximize or minimize an objective function in an application situation. Cheers.